All right. Thank you for coming. Welcome to Scientific Unit Testing. I'm Dave Steffen, tech lead at SciTech. We are a small defense and aerospace contractor. I work out of the Boulder, Colorado office, which is about an hour's drive north and west of where the conference was last year and where we hope it'll be again next year. The PhD is in physics, which is relevant, because what I'd like to talk to you about is the close relationship between unit testing and experimental science. And that's kind of an odd topic. So we'll start out with some ideas that'll lead me down this rabbit hole. So I'll try and take questions as we go through, but we probably won't have a lot of time. So I'll try and take questions at the end, and I think we put up in the chat where we'll be afterwards, so people can come find me and ask questions. All right, so, right, first of all, I'm a physicist. I have to quote Newton. I'm not sure I've been standing on the shoulders of giants for this, sitting on their shoulders maybe, lying in a hammock that they're carrying around. But my job is much easier because you've already heard a whole lot about unit tests this week. And you've gotten a lot of good advice, okay? And if you look through previous CppCon talks and other conference talks, there's a whole lot of good advice out there. Earlier this week, you got test-driven development from Phil Nash. Claire talked about acceptance testing for GUI. Ben Sachs did a kind of getting started beginners back to basics talk yesterday. Also, let me call out, because I'll refer back to this, one of my favorite talks, Titus Winters and Hiram Wright. All your tests are terrible. This was CppCon 5 years ago. It's one of my favorites. I make all my my team members watch that. And also I liked Fedor Pika's, his Back to Basics talk last year. Very information dense. If you're new to unit testing, bite that one off in small pieces, okay? And also Kevin Henney gave these two talks, which were my introduction to behavior-driven testing. I was late to that party. So these are a couple of talks, and you can look, all of these talks are up on YouTube except the ones from CppCon, which will be up on YouTube in a month or so. And there's all kinds of other places. There's talk after talk after talk up on YouTube about unit testing, blog posts, books. There's all kinds of great stuff out there. So just to kind of get started, there are a lot of properties of unit tests. Different people have different lists. This list was more or less, I think, proposed by Titus and Hiram 5 years ago. Ben talked about this quite a bit yesterday. What you like in your unit test: correctness and completeness, readability. Unit tests typically don't get tested in and of themselves, so how do you know they're right? You declare them right by inspection, which means they have to be inspectable. Demonstrability, you want them to be able to demonstrate the proper use of your code. Resilience, you don't want them to break under maintenance, all these good things, okay? But if you go look anywhere else, there's all kinds of other good advice. You want your tests to be easy to run. You want them to be fast to run so you don't slow down your teammates in your development cycle. You should use test-driven development. Go see Phil Nash's talk earlier this week, and he's given a bunch of other talks on the subject. You want your test to be deterministic, okay? You may have code coverage or regulatory requirements depending on what your industry is, okay? There's a couple of these that I want to drill into to kind of see if we can find what's sitting behind a lot of this good advice. But before we do anything else, the most important thing is rule zero, existence. Your tests have to exist, all right? All of this advice that you've been hearing can be very intimidating, especially if you haven't done unit testing before. And you can never get all of it, okay? You can never meet all of these things. You can probably mostly meet most of them, but even if you can't meet very many of them, write tests anyway, okay? Bad tests are almost always 1,000% better than no tests at all. I've seen negative value tests once in an extremely dysfunctional environment, okay? So write your tests. All right, let's jump right in. The most common advice for testing object-oriented code or just testing a class is to do so-called black box testing, where you use only the public interface. Black box, because you're not looking in to see how all the gears and the wires are laid out, all right? You're not looking at the implementation. You're just looking at the external behavior of the thing. And there's all kinds of reasons for this. And there's all kinds of talks and discussion about why you should do this. It forces better design, because you wouldn't have designed it that way if you'd known you had to test it. You avoid tight coupling to your implementation, so you can refactor your code, but you don't have to change your unit tests. So fine, so this is the good advice. Let's actually try and go do this and see how much trouble we can get into. Now, this is an example. I didn't so much borrow this from Kevlin's talk. This is kind of wholesale theft. Kevlin, I think I owe you lunch. So we have a binary cup class. It's either empty or full. The default constructor makes an empty cup. There's an isEmpty member function, so you can decide, you can tell if it's empty or full. Filling an empty cup fills it, drinking from a full cup empties it, and you've already written the implementation for this in your head. Everyone knows exactly what's inside this class, right? It's trivial. You couldn't think of a simpler class to try to test, all right? So let's actually go try and do black box testing on this like everyone tells us to. Now, the old approach, which I used to do before seeing Kevlin's talks, was that for every member function, I would have a test case, right? Or maybe a couple if you want to separate out the error cases or something like that. But generally, you've got a default constructor, so you have a test case for the default constructor. You've got an isEmpty member function, you've got a test case for the isEmpty, all right? Now, this is actually not a good idea, and we'll find out why, but this is the way I used to do things, okay? But let's actually go try and do this. All right, here we go. So here's our test case for the default constructor. What do? We make a cup with the default constructor, and then we use the isEmpty member function to see if it's empty. Great, it passes. We're done. Now we go on to test the isEmpty member function. We make a cup, which is supposed to be empty, and then we call isEmpty and we say, wait a minute, there's something wrong here. We just wrote the same code twice. Why did we write the same code twice? And the answer is that you need each member function to test the other one. Okay, you can't test either of these member functions in the absence of the other one, because all you can do is use the public interface, all right? I call this the black box conundrum. Fundamentally, if you test via the public interface, you have a circular logic, or at least a circular trust problem, right? In order to test this part of the interface, you have to use this part of the interface. So you're basically assuming it already works. At some point, you'd like to test this part of the interface, but you probably use this part of the interface to test that. So at no point do you ever really have an independent verification that any given part of this thing works. Okay? For all you know, there's just a bunch of bugs in it that happened to hide all the other bugs, right? And if you've been around for long enough, you've seen this kind of thing. All right? Now, there are many common solutions. This isn't a new problem. People have known about this for a long time. And one of the most common is that people just ignore it. And the joke is that actually that's not such a bad idea. You're supposed to test this way. People go test this way. They get on with their lives. Fine. Now, there's another way that people try and handle this, which is where you declare one member function correct by inspection, and then you start from there, and then you test everything in terms of that, and then you build up a non-cyclic trust graph or something. For example, the isEmpty member function, it's just a one-liner. It's a simple getter. That can't possibly go wrong, so you look at it and fine. At least philosophically, there's a problem here, because you have now introduced a manual step into what's supposed to be an automated system, but okay. And a lot of people do this, honestly. They look at this and they say, well, this is dumb, right? Look, I know perfectly well what I'm supposed to be testing, okay? I know perfectly well what I'm supposed to be testing. I should just be able to reach in here and check the internal state to make sure that the internal state is what it's supposed to be. Then all these problems go away, okay? This is basically white box testing. We somehow open up the class. It should be clear box because you can see inside it, but okay. So you're looking inside the class at the implementation and all where, the gears and the wheels and the belts and the wires to see what it's doing and making sure that that's correct, okay? Now, you're not supposed to do this. You're supposed to do black box testing. But nevertheless, a lot of people like to go do this. Now, what we've got on screen here, of course, won't compile because isEmpty is a private member function, but that's no problem, right? Everyone just does this, right? Define private public, and this compiles, and you can write all your tests. Please don't, all right? Like really, please don't do this. This is formally undefined behavior. There's actually a statement, I think there's a sentence in the standard that says this is undefined behavior. If your testing scheme involves invoking undefined behavior on the first line, I think we have problems, okay? But I do have to say about this, I hate to say it, but it works. At least on a lot of compilers, GCC, I'm pretty sure it does, I think Clang, for obscure reasons, but this actually does work reliably and it's cheap, right? You can get right in, write your test. You don't have to change the original code. You can just get on with your life. Don't do this. If you have to do white box testing, and there are times when this is your only good option, remember rule 0, you have to write tests, okay? You break and caption encapsulation using a friend class. So over here, I don't know if you can actually see my cursor. We had a friend declaration. And then what we do is you define the friend, the cup tester, whatever it is. You define that in your test suite. And then because it's a friend, it can get in and fiddle around with the guts of your cup class. Now you can do white box testing. This is better than the other way because there's no undefined behavior. I suppose you have to change your source code. You had to add that friend class or friend struct, but it's probably not important. I don't think that changes things in any way that matters. People debate this, but nevertheless, I mean, however you do it, all right, this is the better way to do white box testing, but we'd still prefer not to do this. But again, realistically, there are times when this is your only good option. Example, you got legacy code and the code is written in such a way that you can't write unit tests for it. You'd like to refactor it so you can write unit tests, but you can't refactor it until you've got unit tests. So how do you break the Gordian knot? Well, you start with white box testing, you get some tests around it, then you can refactor it and hopefully you can fix it later. But you don't want to do this if you don't have to, and it seems odd that we are incapable of actually following everyone's good advice to say not to do this. What are we doing wrong? Okay, why didn't this work when we tried to do it before? Now the answer is this thing called behavior-driven development, okay? The idea is that we don't do this. We don't have one test per member function, all right? What we do is we test the class as a whole and we have a unit test for each behavior. So the behavior of the whole cup is that a new cup is empty. And an empty cup can be filled, and filling an empty cup makes it full, and drinking from a full cup makes it empty, and et cetera, et cetera, et cetera, all right? These are what you're trying to test, okay? And if nothing else, you notice that the names are now much, much better because your unit test names now read like the design spec, and I've seen that be very, very useful in real situations, all right? So let's actually go do that and see how much trouble we can get into. So here's our test case for a new cup is empty. Great, we make a cup with the default constructor and we require it's empty. Okay, that's what we're supposed to do. Great, and we go on to an empty cup can be filled. And now you say, wait a minute, back up. Didn't we just do this? I think we had this exact code 2 or 3 slides back. We actually wrote it twice and we didn't like it either time back then. Why is it okay now, right? All we've done is change the name, all right? Why does behavior-driven testing solve this black box conundrum, all right? Don't we still have that circular trust problem? The answer is that we are testing the behavior, not the implementation, okay? We're testing the consistency of the interface, not the correctness of the implementation. And I had to repeat this to myself for a day or two before it really sank in, okay? We're testing only the behavior that is visible from outside. So look, if the constructor is wrong, because it gets the logic backwards, it gets the sense of the internal Boolean backwards, right? Makes a full cup. But is empty is also wrong and flips the logic. And fill flips the logic, and drink flips the logic, and every other member function flips the logic in such a way that from the outside, it actually looks like it does what it's supposed to do. It's correct, right? I mean, even if internally, it's just a flaming pile of bugs, and it's incomprehensible and whatever, you have to declare it correct. Like, on what basis are you going to say it's wrong? Okay? Black box testing isn't asking whether you like the implementation. That's what your code review process is for. Testing is just to see if it's correct. And if everything it does is correct, I think you have to declare it correct, okay? A bug that cannot, under any conditions, be observed isn't really a bug. Okay, and now at this point, the physicist gets interested, and this is where the hole gets deeper and you've got like red pill or blue pill things going on, okay? If a bug that cannot be observed under any conditions is not a bug, a physicist will remember that about 100 years ago, a little bit more, we had a problem in physics. You'll remember there was this guy named Maxwell, and he comes up with the equations that unify electricity and magnetism, right? And out of that comes the fact that electromagnetic radiation is a wave, and that's light. Hey, this is fantastic. We now understand all these things, but there's a problem, all right? Waves in water have a speed with respect to the water. Sound in air has a speed with respect to the air, but light goes through vacuum. So what does it have a speed with respect to? Nothing? That doesn't make any sense. So at the time, this is late 1800s, very early 1900s, they came up with this new idea that there was some stuff out there that we had just never noticed before. They called it the luminiferous ether, all right? And this is some stuff that pervaded all the space, and this is the stuff through which light propagated. And they said, okay, we've got this theory that says there should be this stuff. Let's go measure its properties. And every time they tried, they failed and got 0. Right? Famous experiment tried to measure our velocity through the luminiferous ether. And every time they measure it, this is the Michelson-Morley experiment, I think they got the Nobel Prize for this. They got a velocity of exactly 0, despite the fact we know that our planet's spinning, right? What's up with this? Well, the answer was that the luminiferous ether, if you're moving through it, does things. It shrinks your meter sticks and it changes angles in your experiment in exactly the right way, such that you can never measure it. And this kind of stumped everybody until this fellow named Einstein comes along and says, wait a minute. A physical phenomenon that cannot, under any circumstances, be measured doesn't exist. Unit tests, the bugs that cannot be measured don't, right? It's the same argument, right? If you can't measure it, whether it's there or not shouldn't matter, all right? So Einstein throws that whole idea out, comes up with the special theory of relativity, stands science on its head, and gets a Nobel Prize for something else, which was actually getting quantum mechanics started, which turned the rest of physics on its head, okay? Because he was that kind of guy, all right? Science has been here. Now, aside from the revolution in physics, everybody had to go back to the drawing board and revisit the underpinnings of physics. What is the philosophical basis by which we decide that we know things, we know what's true? And out of that comes a stronger foundation for modern science. And a lot of that rests on something called Popper's falsifiability criterion. What science would like to do is make statements that are true, that can be proven true or be proven false, and then go prove them true or false, and you're done. But in general, you actually can't do that. Think Newton's theory of gravitation, which says every object in the universe attracts every other object in the universe with a force proportional to a bunch of math. And we're going to claim this is true of every object in the universe. Every object in the universe? You can't go check every object in the universe, right? There's some object 44 billion light years away at the edge of the observable universe. We can't go look at it to see whether it obeys these rules, okay? It just can't be done. So what science realized is that we have to do the next best thing, all right? We can't prove things true just in general, very rare cases. But you can do the next best thing, which to make statements that can be proven false, you try to prove them false and fail. And the harder you tried to prove them false and fail, the more you think that they're true. In other words, your confidence that the statement is true tracks the thoroughness of the tests which didn't prove it false, all right? Now, if we apply this to unit tests and go back to where we started just a little while ago, we were saying that if a class exhibits correct behavior in every circumstance, you have to declare its implementation to be correct, even if the innards are a flaming pile of self-contradictory bugs, all right? What we're doing is we're making a falsifiable hypothesis, which is this code has no bug. Then we write tests to observe the bug. We fail to observe the bug. There's no bug. And the confidence in the correctness of your code tracks the completeness of the testing of your code, all right? Now, what we just did is took something out of the philosophy of science and applied it to unit testing and learned something. Now, if these are similar, do we learn something by turning it around and seeing if the metaphor works the other way? And actually, we do. If you think about what empirical science has been doing, we are trying to reverse engineer the source code of the universe by writing unit tests against its observable behaviors, right? This is what an experiment is. You observe something in the universe, and then you try and figure out what's going on. And scientists would love to white box test reality, okay? We'd love to know what's going on. Quantum mechanics is so bizarre, the more you know about it, the less you think you understand any of it, okay? We'd love to white box test reality, but we can't, because no one's figured out how to define private public before we include reality.h, right? We can't do this, all right? So what we do instead, and have been really doing for the past 350 years or so, is developing experience with the logic, procedures, and epistemology, that is the philosophy of what do we know and we don't know and how do we know it, of black box testing. That's what empirical science really is. So the first result is that behavior-driven black box testing is on sound philosophical foundations. Thank goodness for that. I'm sure many of you out there were losing sleep at night worrying about this. Now we can actually get some sleep. You guys won't worry. No one else worries about this. But look, can we get any practical results out of all of this? For example, if you start to think about it, your software is a system. It's a physical system, right? I mean, there's electrons getting pushed around at some level. It's a physical system that you want to poke, prod, and study for the existence of bugs. And your unit tests are the experimental apparatus to detect the bugs, all right? That's really what we're trying to do. If this is the case, maybe experimental science can give us a few pointers, all right? So here's the simplest example I could think of. How do you measure something on a scale? Alton Brown, we're fans of Alton Brown. His formula for coffee is 28.5 grams of coffee to 400 grams of water. My wife and I do 30 grams because we live on the edge. Do you think this is 30 grams of coffee? Are you sure? Do you think maybe this is a trick question because I'm asking at the CppCon conference? You should at least be thinking about, whether or not, whether or not the mass of the measuring cup is included in that 30 grams, right? In fact, this measurement is completely meaningless. I don't know if you can see it on your screen, but that button right there is labeled 0. All good scales have a way to zero them at some condition, and then they measure relative to that. If you don't know where this was zeroed, you have no idea what this means, okay? And hint, this is not 30 grams of coffee, all right? What do? All right? You zero the scale out, but you do it under exactly the same conditions, right? There's a sample and you want to measure the mass of the sample. So you set everything up exactly the way it's going to be, but without the sample. You zero it there. Then when you add the sample, you have reason to think that that 30 grams really means you've got 30 grams of stuff. And by the way, that really is 30 grams of coffee. I hope you've gotten enough coffee today. I can't give you real coffee because it's a virtual conference, but you got a picture of it. And I've got news for you. This is test-driven development. What do you do in test-driven development? Okay, you write a failing unit test to demonstrate the bug. You fix the bug. You rerun the unit test and watch them turn green, right? The sample you're measuring is your bug fix. Okay, so first, you measure the system without your sample, without the sample, which is without the bug fix. So the test fails. You introduce your bug fix, all right, which is introducing the sample, and then you measure again, and you measure the results of adding the sample. In the presence of the bug fix, the bug is not detected, all right? Test-driven development is just good lab technique. It's not just, all right? There's no just there. It's good lab technique exclamation point. And honestly, test-driven development is a whole lot of other things. Go see Phil Nash's talk earlier this week or at previous conferences. My favorite statement about test-driven development came from Fedor Pikas at his Back to Basics class last year. It's not so much about what it does to your code, it's about what it does to your mind. Now, this is a talk about science, and I think Fedor is talking religion. But he's not wrong. I love it. This is absolutely true, okay? But this aspect of test-driven development is basically just the discipline to make sure you're doing good lab technique. Now, by the way, something else you do if you need to measure things is you calibrate it. You put a known weight on the scale, and these are typically expensive because you have to trust them. And then you make sure that your scale reads what it's supposed to read. Is there an equivalent in unit testing? Yes, and actually Ben talked about this quite a bit yesterday. Once you've got everything working, you should go break your code and make sure your unit tests fail the right way, all right? Introduce known bugs and watch your unit test tell you about them. Most people don't do this much, but I found this every now and then useful, particularly for beginners. It can be very confusing if you're writing unit tests to test failure modes, right? Because the test succeeds if the code fails, but only if it fails the right way, and the test fails if the code succeeds. What? Well, sometimes, like if you've got a bunch of different exceptions that can be thrown, it's really useful to go in and change the type of an exception and watch your unit testing framework catch the fact that you just threw the wrong exception. That kind of thing is basically just calibrating your scale. Okay, let's go on to another example. This is a little bit more pernicious. What is the definition of right? Okay, so we've got some floating point code, all right? This is not interesting floating point code, and it's a stupid example because it's a slide, and I don't want to have to explain complicated floating point. We're trying to compute some number, which happens to be pi. We compute it by taking the arc cosine of -1. Notice that there's an f at the, it's up there somewhere. ACOS F, right? That's single precision floating point, okay? So the answer is only correct to 7 decimal places, about what you expect, right? 3.141592 is correct, that 7 is wrong. But if it's some real computation, you don't know what the answer is, this is probably good enough. Well, maybe it's good enough, all right? If you were trying to measure this or compute the equatorial circumference of the Earth based on this, you're going to be off by at most a meter. And I've got news for you, but the Earth's radius is only known to about 7 decimal places. It doesn't have any more accurate one because we've got solid tides. Never mind the tides in the water. The continents flex. And at the equator, the continents, the rocks go up and down by about half a meter anyway. This is fine, all right? Your floating point computation works. It's good enough for your answers. Your system is fine. Everybody's happy until someone comes along and takes that F off. They improve your floating point computation. Now, the result of this is good all the way out to 16 decimal places or whatever your machine supports, but your unit test just broke because you've got extra digits there that are now wrong. But you didn't need those digits, right? Those were kind of garbage, right? They didn't matter because the rest of your computation was only good to 7 decimal places anyway. The point is that an incorrect right answer creates a brittle test. It breaks under maintenance because you've unnecessarily pinned your answer to a specific algorithm as opposed to the general thing you're trying to do. This is just bad error propagation, which is the bane of all freshman physics labs, and I've taught many a physics lab, nobody ever gets it right. Okay, you've got your measurements, the input, okay, and there's only so many important figures in there that actually mean anything anyway. Then, as you go through your floating point computation, you're gonna lose some of those significant figures due to round off, and at the end, you're gonna get something, and it's right, well, we hope it's right, but it's either right based on what you put in, and you can say this is what we should get, or it's right enough for what you're trying to do, okay? So, the fact is, oh, by the way, what should be done here is that you use something in your unit test framework to do correct floating point computation. All good unit test frameworks have one. Developing mathematical algorithms, that's hard, right? Characterizing the numerical stability and the round-off error is even harder. But it's actually part of the job, right? You don't really understand it. You shouldn't rely on it. You probably can't code it right, and you might not be able to test it right unless you've actually done all that work, all right? You have to figure out what the error bars on the end are and then put those into your unit tests. And this isn't just floating point, okay? 5 years ago, that talk, all your tests are terrible, Titus and Hiram make a lot of fun of someone who is testing a JPEG compression. They take an image, they JPEG compress it, they get a result, they put that into the unit test. They run the unit test and they get the right answer. Hurrah, it works. No, it doesn't, because someone goes and improves the JPEG compression algorithm. Same thing happens. The test fails, although something else got better, okay? So even if you're not doing some fancy floating point computation, you still have this problem. What is the right answer? I don't know how you decide whether a compression algorithm does a good job on a picture. Is it good enough that the human eye can't detect it? How sensitive is the human eye to green light? I don't know how to do that. That's hard. But if you're writing JPEG compression algorithms, you probably need to think about it. Okay, let me talk for just a second and check questions. Let's see. I will just mention, I'm talking about unit tests. Yeah, everything we're talking about is just testing in general. Unit testing was just kind of the hook, maybe, or it was the easy example to get started in, because that's what everyone's worrying about right now. Okay, let's get more general, all right? Now, we can't go into like the full theory of experimental setup, right? That's a big topic. And by the way, my PhD was in theoretical physics, right? No one wanted me in their lab. I walk in and things blow up, right? I stay away from the experiments. But roughly speaking, for our purposes, we can say that 3 things we want out of a good experiment is it's precise, it's reproducible, and it's accurate. So let's talk about these. All right, now what precision means in this context is that any given measurement gives you a lot of data, all right? You get a lot of information from doing whatever it is you're doing. So the most obvious thing here is just use a unit test framework that gives you good messages, and make sure you're using it to give you good messages, so that if something fails, that is, if you detect a bug, right, it tells you, here's the file, here's the test case, Here's the line number, here's the assertion that failed. We expected 49, we got 42, whatever, all right? You want a lot of information that points you directly towards what the problem is, so you don't have to spend a lot of time understanding that. You can get straight to understanding the real bug, all right? That's precision. That's a precise experimental setup. But here's another, maybe more pernicious. You will see this every now and then. You've got a test case for a widget. I don't know what a widget is. It's anything, and as a part of that, we're going to put some widgets in a vector. So we make a standard vector of widgets, and then we require that it's empty. We test that, right? And then we push back in a widget, and we make sure that it's got size 1. Really? Now, you will actually see this out in the big wide world for all kinds of reasons. The reason why this is bad isn't because it's silly to test standard vector. Someone's got to do it, right? You hope that the people who wrote it. But change the example a little bit so that instead of standard vector, it's some other thing, it's some dependency that's maybe it's developed by the other team down the hall, who are a bunch of knuckleheads and they never write good unit tests, right? And so you want to make sure their stuff works so that you can make sure that your stuff works. So you're going to write a test for it. Fine, don't put it here. The reason you don't want to test their code in your widget test case is that if they break something, the widget test case turns red, which means that at 2 in the morning, when there's a production break or something goes wrong, they're going to call you because the test report says something broke in widget. Test this if you want, but put it somewhere else where it says we're testing standard vector. So if it breaks, they go bug the right people, okay? This gives you an imprecise result because it's pointing you at the wrong place. Don't put red herrings in your path. Okay. Reproducibility, this is a little bit more complicated, all right? Most scientific experiments out in the real world have measurements or noise or whatever. You do the same experiment multiple times, you don't get exactly the same answer. Now, most of the time that's just interference from the environment, it's noise, there's static on the line, or someone bumped the table or whatever it is, all right? But sometimes it's because you're studying a complex system and you can't control for everything. Think testing a medical device or a new drug or a new therapy, right? You can't just do it on one person because biology is really complex. You need to do it across a bunch of people to see whether the thing works or not, all right? Or think about any psychological experiment where you're trying to tease out underlying things across human brains, right? We don't even know how many, we can't even hope to characterize that right now. So it may be that you've got so many variables, you can't eliminate them. And so you have to put up with getting some randomness or something. Or maybe it's built into the system. Quantum mechanics is going to give you random numbers or random answers. That's why it's so weird, okay? So science has developed ways to handle this. And the 4 obvious ones are that you either do a better job of isolating yourself from the real world. You measure the signal you don't want and subtract it. Think noise canceling headsets, right? There's a signal you want, there's a signal you want. You have a separate thing to measure the signal you don't want, and you subtract it. If you can't do those, maybe you can at least detect that there's a problem and eliminate the erroneous results, mark those as, hey, that doesn't make any sense, and ignore this. Or the last case, everyone's last ditch effort, is statistics. Now, this is about handling interactions between your test and the environment, okay? I'm not talking about code that's non-deterministic for good reasons. If your code depends on a random number generator, well, you're going to get different answers every time you run it, okay? So what do you do about that? Well, you seed the random number generator to the same number every time before you run your unit tests. Or maybe you have to mock your random number generator so that it's deterministic and you don't have this problem. But sometimes you can't get rid of it. Like, what if your code is a random number generator? Or what if it's a driver for some piece of hardware that's an entropy source to generate true random numbers, right? Well, in that case, what you have to do, this gets back to what we just talked about. The correct definition of your answer isn't a given sequence of numbers because you can't rely on that. Your unit test has to do the statistics to make sure your random numbers are right. But that's kind of a separate case. What I want to talk about here is interference from the environment, okay? Tests should fail because the code under test fails and for no other reason. That's the ideal, but we all have experience with unreliable or flaky tests. They depend on timing or some external state. There's a test server that's down, there's a file system that's full, something like that, that leads to erroneous test failures. And the first thing to do if you're tackling this is to make damn sure that the non-determinism really is external, that it isn't your code broken, all right? We're assuming that as we go forward, right? You have to absolutely prove that these are false alarms from the external world. So the first thing you do is isolation, right? That's easy unless your code is code that's explicitly supposed to go out and touch the real world. Connecting to a test server, connecting to a database, writing to a file system, all right? What do you do if the code has to go interact with the external world? Well, you can mock the external thing. So you're not really touching the external thing. You're touching an internal thing that looks the same, right? Maybe you fork your process and create the external thing in the other fork process, but maybe you've got more control over it. Maybe that could work. You know, you fork a process that fires up the server and then you communicate with it. More likely, you've got dedicated test servers or dedicated test databases or dedicated file systems that are there just for the purposes of your testing that you can rely on. Okay, if you're running on hardware, hopefully you're running your tests on your hardware. You might have to have a bunch of dedicated hardware instances for your CI pipeline to hit as it's running your unit tests, all right? This can be expensive. It's expensive in science too, right? People build physics labs 600 meters down in old disused salt mines to shield it from cosmic rays, okay? It's pricey, but the alternative is that you've got tests you can't rely on. So that's one option. Now, if you can't do that, maybe you can subtract out the problem, all right? I don't know that this is generally useful, but at least in principle, if you're supposed to connect, say, to a server, and your unit test depends on this happening within a certain period of time, you build some external sensor and you verify that independently, all right? And it's there just to measure the latency to the server. And whatever it measures, it cues your unit test framework or your test framework in general to say, hey, the server's slow today, add 2 seconds onto everything, so that your tests can adapt to the external situation and still give you answers that mean something. Might be useful, might not be, but it's an option, okay? Now, the other option, if you can't do any of those, is at least you can detect the problem, right? You've got your external sensor that detects, hey, the server's down, the database isn't there, the file system is full, whatever, and you use that to cue your unit tests that test can't be run or the result you just got is invalid, okay? Now you can do this, but you also have to have the tools and the processes in your team to deal with what happens when it says, hey, I can't run the unit test, okay? If the environment invalidates the test, hey, the test server is down, all these tests are gonna fail, but it's not the code's fault, right? What do? Maybe you mark them as pending and you rerun them later. You hope the test server comes back up, okay? Or you mark them as not run, and then you have to decide in your team what to do about it, right? Can we merge this pull request if it's got something marked as, hey, we couldn't run the test, we're gonna do it tomorrow? If you can't do that, you're gonna have a whole bunch of pull requests piling up in your team waiting for test resources, at which point, haha, it's always good to go to management with real numbers and you can say, hey, we need more resources for our test environment and I can show you exactly how much time it's costing. All right, finally, if all else fails and your back's really up against the wall, you can do statistics. All right? You can collect some samples and you might know, hey, this test fails 1 out of 5 times. So you rig your test framework to say, well, it just failed, let's run it 4 more times and see what happens. I mean, roughly speaking, more than 4, right? But you rig your test to know that, hey, it fails every Thursday night, okay? So if it runs on a Thursday night, I'm gonna rerun it later or something. It's kind of a last-ditch effort, but it does give you one very useful thing. You're automating the ignore that flaky test failure, because that way your engineers don't get desensitized to it, right? If you've got a test that just fails every now and then, everyone gets used to looking over, oh, it's that test that just failed, I don't care. And at some point, it's gonna be some other test, but they're gonna ignore it because it looked the same, right? Don't desensitize your engineers to flaky tests. If possible, rig your testing system to handle that. Okay, now this is the last thing we're gonna talk about. This is accuracy, which is a bit more complex. And what accuracy means is that the results of your experiment match reality. So we have a truth table. Everyone likes truth tables, right? We've got 2 binary options. Your code's correct or it isn't. Your test results pass or maybe it's over here. Test results pass or they fail, okay? So the first thing is we're thinking of our labs as test equipment to detect something. And the thing we're trying to detect is bugs, but we're making a falsifiable hypothesis, which is that our code is correct, and we're trying to detect a signal that says otherwise, right? So positive in this context means you found a bug, and negative means there's no bugs. Now that's the emotional opposite of what you want, right? No bugs is positive, makes you happy, you can go home. You find a bug, you're unhappy, you have to stick around, and it's late, but you gotta fix the bug, all right? So this isn't the emotional response, okay? This is there a signal? Positive means there's a bug, negative means there isn't a bug. And in this table, I've labeled 2 things in green and 2 things in red. Now the green ones are the high accuracy results. your code is correct and your test results pass, or your code is incorrect and your test results fail. Those are the cases where your tests in reality match. And those are green. And the other two cases are red, because that's what we don't want, okay? This isn't the same colors that your CI pipeline spits out if it finds a failing test. Those are the numbers over on the left, okay? So this is a little bit more complex. Let's go through each one of these in turn. So upper left-hand corner, high accuracy, the position we all want to be in. Your code is correct and your test pass. Hurrah, success, okay? Why have you gotten here? Because your tests are complete, they're correct, you've got the correct definition of the correct result. All these good things that everyone's telling you to do, you've done, and your code is correct and your test results tell you that your code is correct. This is a success, ship it. Fantastic. Now let's go down to the false positive case, all right? False positive means your code is correct, but your tests fail. How does this happen? Brittle tests. Someone fixed something and broke it. This is the example before of the correct definition of the correct answer, all right? Or you're depending on non-guaranteed behavior. You're depending on the order in which you iterate through something in a hash structure or something. Or it got broken under maintenance, or you had insufficient test reviews or something. The point is the code is correct, the test is wrong. This is a false alarm. And the cost of this is wasted time, because you have to go fix something although your code's correct and you could ship it. So that's a false alarm, okay? Now to contrast that, let's go upper right. This is the other low accuracy, poor accuracy case, which is your code isn't correct, but your test pass. What's this? Well, your testing was incomplete. Some bugs were hiding someplace, but you didn't shine the flashlight over there, or you're testing in an unrealistic situation. There's a whole area of the room that you didn't look in. Or you got an overly generous definition of right. You opened up your error bars too much, and you're looking right at a bug, but you can't detect it, all right? You can't recognize it. This is an undetected bug. The risk here is that you ship something that isn't going to behave properly. Now, just briefly, let me point out that people are very rarely over in the upper left-hand corner where everyone wants to be. I mean, maybe you're there, but at some point or another, you're probably going to be in one of these other cases where you've either got a false alarm or an undetected bug. Fixing that's hard, but at least you really ought to know which one of those is important for your industry, okay? If you're building a video game, right, shipping on time is important because you've had months of advertising and it costs you a lot of money if you don't ship. If there's a bug on level 57, no one's going to get there for weeks anyway. You can patch it, right? No big deal. So you'd much rather ship with bugs than miss a ship date, all right? On the other hand, if you're building flight avionics or a medical device or something, you're happy to miss a ship date. Well, I don't know about happy, but you're happier to miss a ship date than you are to ship something with a bug in it. And if you start reading about this, reading gets very grim, all right? Go back and look at the Patriot missile system in the Second Gulf War. Partly due to software errors, we had 2 friendly fire incidents, all right? Or if you really want something grim, go look up the, it's the Therac-25 computer-controlled radiation therapy machine. It's a cancer treatment machine. And on several cases, because of software issues, it delivered massive overdoses of radiation to cancer patients, killing 3 people, all right? This is grim, but those of us who work in that this absolutely has to work or someone dies, you don't want to be in this situation. Now, you may not be able to avoid having accuracy problems. In fact, everyone's going to have them at some point, but knowing which position you'd rather be in tells you where you can spend those precious and scarce engineering resources to fix things, okay? It's very important to know which one you'd rather be in because you can spend money and time making sure you're in the one that you can live with. All right, finally, let's go to that one down in the lower corner there, all right? Now, this is in green, although you may not be happy about it, but this is a success. Your code is incorrect. Your tests fail, that's a success, all right? Your test just did what you wrote them to do. They told you that you have a bug. This is success. Now, I'm not saying you're happy about it. You may be very unhappy about this because you wanted to go home or you wanted to close the ticket. But this is a success. It needs to be celebrated as a success by the team. It needs to be celebrated as a success by your management, all right? And if it isn't treated as a success by your management, you might want to look elsewhere. We're hiring, okay? And I've been at places where this was a problem and it's like, this is not going to lead to anywhere good if you are in some way punished or the results are bad, that you found the test, that is to say, you found the signal from your experimental lab setup that you were trying to find with it. Now, this is really where science gets interesting, all right? My favorite quote about science actually comes from Randall Munroe, the guy who writes the XKCD comic. And if you don't know about that, go there because he's the only person who makes funny jokes about computer science. But this is what he said. You don't use science to show you're right. You use science to become right. This is a very profound statement, and I can't tell you how true it is, all right? This is how science works. And if we swap out science for unit tests, we still get a very important statement. You don't use unit tests to prove that you're, well, actually we do, okay? We do, but that's not really the point, all right? We use our unit tests to become correct, right? No one gets to that upper left-hand corner where we can ship it, where everything's correct and your tests prove it and all that, without having been down here a lot and finding all the bugs we didn't think about because you wrote good unit tests, all right? So if Fedora can get religious about test-driven development, I can get religious about this and say that this result is enlightenment. You just learned something you needed to learn. You're not happy about it, but you learned it, and that is absolutely crucial if you want to move from this form of accuracy to the other form of accuracy, which is where everybody wants to be, okay? So that's accuracy. Let's try and wrap this up a little bit. Unit testing is science. Again, it's a physical system, and what you're doing is building a lab setup to measure a specific thing about that system, which is, do you have bugs? Not just unit testing, all of your tests, all right? What you're doing is making a falsifiable hypothesis, call it C, all right, that this code is correct. You then write unit tests and attempt to show that it's wrong. Go find the bugs, all right? Your confidence that C is true tracks the thoroughness of the test you've used to try to prove it false. This is the scientific method as understood by modern philosophy, okay? Now, all of that advice you've been getting from all the other talks, all that stuff, I put up that slide at the beginning with all the stuff on it. You go listen to the other talks, all the blog posts. Is there some place kind of underneath that we can look to see where all that's coming from? And I think there's 2 or maybe 3 places. A lot of that advice comes from necessary process. Test-driven development is a necessary process for a lot of reasons other than it makes you zero your scale, okay? Making your tests run fast so you don't slow down your team's development cycle. Maybe your industry has regulatory requirements for unit test code coverage. And so your company says, look, you must do it this way, okay? Or it might be maintenance issues. This is what the guys from Google and the guys from Bloomberg are usually talking about. How do we write these tests so that they're still true and useful in 5 years and they don't represent an enormous maintenance burden on the development of our code, okay? That's really important to do, all right? Most of black box testing is really about that, okay? But everything else, I think, this is an unproven hypothesis, tell me wrong, tell me if I'm wrong, but everything else is about making good tests, all right? Because we want to prove that our code is true, and we know we can't, really, right? I mean, proving that your code is correct, isn't that the halting problem? Right, which is NP hard. I think someone with a PhD in computer science can correct me on that. I don't know that stuff. I'm a physicist, all right? But you can't prove it true, right? But you can prove it false. So what we are doing really is science in every way, shape, and form. And given that we've got centuries of experience doing that, whereas we've only got, what, 20 or 30 years of unit testing? 20 years, I don't know, something like that, right? It isn't surprising that we might want to go look at what science has been up to since the late 1600s to see how they handle these problems, okay? A lot of this stuff has already been worked out. We just have to figure out what it means for unit testing. So to summarize, what I'd like you to do with all of this is remember that you must test, right? Even if you can't do all this, go write your tests. You're lost without having good tests. Go forth, write good tests, and do good science. Thank you. Now, I'm looking over here, and I've got question after question after question, which isn't really surprising. Give me just a second here. Let's see, not unit testing. Do we have to use the scientific method in testing highly complex systems? AI that was learning for 10 years. So, okay, you got an AI that's been learning for 10 years. Now, how do you characterize what's true? I think it gets back to that in part. How do you know it's giving you good answers? Well, you can argue that a sufficiently advanced AI is maybe more like asking a person than a computer program, because I don't know anything about AI, but my understanding is a lot of times you've trained to do something, but you don't really know how it does what it does. You just know it's trained and that it gives you good answers. Well, look, you've got developers you work with. They've been trained for years. How do you know they give you good answers, right? You might be at some point reduced to doing psychology on your AI to make sure that it actually knows what the hell it's talking about. That scares me, and there are people at my company that do AI research, and I don't know. I believe that that's a tough question. That's a good one. All right, hang on here. Let's see. Introducing bug checking unit tests is based on mutation. Yes, mutation testing is kind of that calibration that I was talking about. I had the picture of the weight on the scale. It's that written large, and I know nothing about it. But if it's something where you go in and make sort of random changes to your code and watch it break, yeah, that's exactly an extremely thorough calibration exercise to make sure that your tests can catch all the stuff that they're supposed to catch, right? That's exactly what that is. Okay. Yeah, you're exactly right. Let's see. How whitebox testing work with external dependencies like underlying private classes or external devices. Oof. Yeah. So look, black box testing is hard, and it's, I mean, you have to mock things because it depends. I mean, it's complicated, all right, which there are a lot of other good talks about. Start by the talks previous this week. Go to some of those talks I put on my first slide. And by the way, I don't have them yet, but when these slides go up, I'll have more extensive links on this slide after the one that's up. Now, yeah, so there are times when you're up against the wall and none of the good advice works and you have to go do the thing you're not supposed to do, white box testing, all right? I've seen math code that's got a huge chunk of math, and we'd love to break it apart and unit test it to make sure this coordinate transform works and this, but we can't, because breaking it apart makes the code worse and it slows it down because you can't hang on to your intermediate results. White box test, it's your best option. My project right now is an extremely legacy thing, 500,000 lines. There's Fortran 77 in there. You know what? White box testing is great. We have unit tested 0.1% of it, and it's totally saved our butts. But oh, it's ugly tests. But hey, it's what you have to do. Testing hardware drivers for hardware, I don't know about that's a good one. Can you mock it? Can you come up with a piece of hardware that isn't the real hardware but acts like it enough but gives you known results? That's a good one. That's tough. That's a tough one. Let's see. Black box testing. Yeah, black box testing has that worse. White box testing still has it, but at least you can go in and rewire something. Black box testing, yeah, mocks are your first guess. I don't know how much time we've got left. There are some things you can do to your initial design to make it easier to mock or easier to test. And some people will argue, oh, I don't want to test. I've got this beautiful design. I love my design, but it's hard to test, but I don't care. I shouldn't have to test for design. I will tell you, I used to be in that. Way back when, we had this beautiful software that was very carefully designed. It was beautiful and we liked it, but you couldn't test it. And then we started doing unit. This is back when I first started doing unit testing. And we resisted. We started doing the define private public, all right? Because like it's the only way we can't get in to look at what we want to get into. And it took us a while to realize that every time we just bit the bullet and changed our design to let us test it, the design got better in ways that totally surprised us. Design for testability, that's a big design. All the other things you're supposed to do that too. Design by testability isn't an afterthought. If you can design it up front, this makes this at least much easier to deal with. But even then, there are times, okay? There are times when you got to pull out the white box or do something crazy, all right? It happens. When your back's up against the wall, all right, you got to go do it. All right, let me see. Okay, that's all the questions I see right now. I don't know how much time we've got left, so we'll call it good here. I'll meet you wherever we said we're going to meet you in the virtual room. And if you're watching this a month from now on YouTube, Comments down below. Tell me I'm wrong. Tell me I'm right. Tell me that the halting problem is an NP hard, whatever you want to tell me. All right. Thank you very much.